Hello everybody, welcome back to the channel. I'm here with another Head Start to A-Level Chemistry video. In this video I'm going to be looking at Quantitative Chemistry Part 2, which is the triple chemistry GCSE content. That means that this is going to be a really useful refresher for everybody, but if you studied combined science, this is content that you have just completely missed out on, so you need to pay extra special attention here so you are up to speed and ready to make a really good start to your A-Level chemistry studies in September. The first skill we're going to take a look at in this video is percentage yield. Now, first of all, yield is how much of a thing is produced. This can be in grams or kilograms, so a mass, or it can be in moles. We'll take a look at it in mass. So the percentage yield is how much of what you could have got did you get. So a 50% yield means you got half of what you could have got. Now, if we take a look at an example here, let's look at the Haber process. Nitrogen plus hydrogen turns into ammonia. The question could be, if we have 2,000 kilograms of nitrogen and we produce 1,600 kilograms of ammonia, what is the percentage yield? Now, stage one for this is a reacting mass calculation, which I've gone through in my Quantitative Chemistry 1 video, but a quick review. The method to use is the grid method, shown as here, and we've got 2,000 kilograms, which we need to turn into grams, so that is 2 million grams. Divide it by the MR of 28.0 for nitrogen, gives us a moles of 71,428.6. Then we look at the ratio from the equation. The equation tells us that 1 mole of nitrogen produces 2 moles of ammonia, so therefore we need to double our 71,000 moles, and we get 142,857.1 moles of ammonia. Now, since mass is mR times moles, we need to multiply our moles by 17.0, and we get 2,428,571 grams of ammonia produced. And this is the theoretical yield. That is the maximum amount of ammonia that we could make using the amount of nitrogen that we used. However, we are told that only 1,600 kilograms of ammonia was produced. So this is the actual yield. So this is how much we did get. So we could have got 2,428 kilograms of ammonia, but we only got 1,600 kilograms. So to calculate the percentage yield, you do your actual yield divided by your theoretical yield multiplied by 100. So when we put these numbers into our particular situation here, we get a 65.9% yield, which means we got about 2/3 of what we could have produced. So something's gone wrong because we've lost a lot of our potential product somewhere along the way. There could be a few possible reasons for this. We might have a reversible reaction, and we actually know that the Haber process is reversible, so that's likely here. Or we might have some kind of procedural error, so we might have lost some of our chemicals when we're transferring from one piece of equipment to another. Or something unexpected might have happened. The nitrogen and hydrogen might have made something different instead of the ammonia. Or the reaction might just not have been given enough time to finish. That's probably not relevant for the Haber process, but in other situations it definitely will be. The next skill that we're going to take a look at is something called the atom economy. Now, this is almost always expressed as a percentage, and the significance of its value tells us the percentage of the starting reactants that end up as useful product. And so if we take a look at an equation here, which is where ethene is reacting with water and it is turning into ethanol. Now, there is only one product here, so that means that all of the chemicals that are reacted together are turning into useful product because there is only one product. So the percentage atom economy is said to be 100%. However, if there was a second product, some kind of waste or byproduct, then the percentage atom economy would be much less. Now, to calculate the percentage atom economy, what you need to do is take the relative formula mass of the desired products, multiply it by how many times it appears in the chemical equation, and divide it by the total mass of all of the reactants. So that means if there are multiple reactants, you add them all together, again factoring in any multipliers from the chemical equation itself. So if we take this second equation as an example that we're actually going to calculate, we've got iron oxide reacting with carbon monoxide on the left-hand side, turning into 2 iron and 3 carbon dioxide. So if this is a chemical process that is producing iron in the blast furnace, we obviously want the iron, so that is our desired product. So our calculation is that the percentage atom economy is equal to the relative atomic mass of the iron, which is 56, which we need to multiply by 2 because of the coefficient, the multiplier that is present in the equation. So that gives us 112 on the top. Then we need to factor in the total mass of the reactants. So obviously we've got iron oxide, that is one of the reactants. That's got 2 iron in it, so 56 plus 56 plus 16 plus 16 plus 16 gives us 160 for iron oxide. And then carbon monoxide is the other reactant, so 12 for the carbon, 16 for the oxygen gives us 28, but we need to multiply that by 3 for the carbon monoxide's multiplier in the equation, and that gives us 84 in total. So then when we get our 84 and we add that to 160, we get an answer of 244 for the total mass of the reactants. We then need to multiply this by 100, remember, so we've got 112 multiplied by 100 and then divided by 244, which gives us a final answer for the atom economy as 45.9%. And so what that actually means is more than half of the chemicals that we've paid the money for in the first place are lost during this reaction process. The significance of the percentage atom economy is only one of the considerations that people running businesses and industry need to take into consideration. That's simply because of the scale of the process. Any wastage is likely to be scaled up significantly and be much more expensive. So for instance, atom economy is one of the considerations, and low atom economies usually aren't profitable. Unless you can take advantage of a wasted product and find some use for it and sell it on as a byproduct. That doesn't affect the percentage atom economy itself, but it means that a second product turns into something financially useful. It's also environmentally advantageous because it's more sustainable to use a greater percentage of the atoms that you have paid for in the first place. So atom economy is one of the considerations. Another consideration is the percentage yield that we've just looked at previously. Ideally, we want to have a very high percentage yield because again, that means less of the reactants are wasted, and so again, the process is likely to be cheaper and our profits are going to be higher and more sustainable as well, because again, less of our raw materials are being used, and so this is depleting our resources at a slower rate. A third consideration for an industrial process is how quickly is this reaction happening? So in other words, what is the rate of this reaction? It's no good having a process that is a really good atom economy if it takes such a long time to actually happen that you don't really make very much product at the end of the process, because you want your product to be produced at a decent rate so you can sell it and be making profits as your process is ongoing. Linked to that is equilibrium position. So for instance, if you've got a reversible reaction, such as the Haber process that we mentioned before, or the production of ethanol that we mentioned on the previous page, this reversible reaction will definitely not have a 100% yield. Sort of by definition, that is what a reversible reaction is. So if we have a choice between a few different methods of producing the same chemical, the one that has the position of equilibrium furthest towards the products, towards the right-hand side, that's the one that we are likely to go for in the long run. However, It's all very well having a 100% yield if the rate of reaction is too slow. I don't want to have a process that gets me 100% yield but takes 2 years. I would rather have something that gets me a 2% yield but takes me a day. That obviously in the long run gets you a far higher percentage yield. So it's a balance between how quickly you get your product and the yield that you actually get in that amount of time. And the last consideration is to do with waste. Obviously, I've mentioned the environment and how sustainability of minimising the wasted raw materials, but not only that, we've got the use of the byproducts. Again, stop something going to the landfill or any other waste disposal method, and it turns it into a useful product. One example of a waste product in the nylon production industry is ammonium sulfate is a byproduct. Now, ammonium sulfate, you'll hopefully remember, is actually a fertilizer. So even though the nylon production process is all about the nylon that we are going to use for clothes, etc., the ammonium sulfate can be turned into fertilizer to help crops to grow. So that minimizes waste during this process. Now, you weren't required to know what an empirical formula was for GCSE level. You were just expected to be able to work it out using moles, and we'll look at that in a moment. But the empirical formula for a chemical is the lowest multiple of moles for each of the elements appearing in a compound. So for instance, sodium chloride is NaCl. That means there is 1 mole of sodium for every 1 mole of chloride. MgCl2 is magnesium chloride. That means that there is 1 mole of magnesium for every 2 moles of chloride. That is their ratio. It doesn't actually tell you how many there are. That is the simplest whole number ratio that they appear in, 1 to 1, 1 to 2, etc. Now you can calculate an empirical formula by using mass data. If we take a look at this question, it says 65 grams of iron chloride contains 22.4 grams of iron. We can use those 2 pieces of data to work out what the formula of iron chloride is. The method that we need to use is the grid method. So we lay out our mass, AR, our moles, and our ratio as standard. And so iron, we've been told there's 22.4 grams of iron. The relative atomic mass is 56. So moles is mass divided by MR. That gives us 0.4 moles of iron. And then when we do the same thing for the chlorine, we've got 42.6 grams of chlorine. We know that because the total was 65 and we had 22.4 grams of iron. So we look at the difference between the two there to get 42.6. We then divide it by the relative atomic mass of chlorine, which is 35.5, which gives us 1.2 moles of chlorine. And so now our final row is for the ratio of iron moles to chlorine moles or chloride moles. And we can probably do this by inspection, but the method that we need to use is to divide it by the smallest. The smallest number here is, of course, 0.4. So 0.4 divided by 0.4 is going to give us 1. 1.2 divided by 0.4 gives us 3. So that means that the ratio of iron to chloride is 1 to 3. And that means that the empirical formula for iron chloride is FeCl3. Not only can you calculate empirical formulae, you can also work out the molecular formula of something. To do this, what you need to remember is that the empirical formula is the simplest whole number ratio of all of the elements in a compound. You need one extra bit of information to do this, and that is the relative formula mass of the molecule itself. So, for instance, if we've been asked to calculate the empirical formula of a compound containing carbon, hydrogen and oxygen, and we work out that the empirical formula in the exact same way on the previous page is CH2O, if we've been told that the relative formula mass of this molecule is actually 60, we can work out what the molecular formula is going to be. To do this, we've got 2 steps. We first need to look at the empirical formula and find out how heavy that is. Well, carbon is 12, hydrogen is 1, but there's 2 of them, and oxygen is 16. All of this adds together to make 30. So then when we take a look at the MR of the whole molecule and we find out that it's 60, Well, this tells us that the MR is going to be twice as big as 30, and that means that the molecular formula is going to be twice as big as the empirical formula. So the general process is you take the MR, you divide it by the mass of the empirical formula, and the integer value that you get out of that, that is a number that tells us how many times bigger the molecular formula is than the empirical formula. So 2 in this case. And so that means that the molecular formula is C2H4O2. If we had the same empirical formula, but this time we were told that the MR was 180, we do the exact same process. We take 180, we divide it by 30, the mass of the empirical formula, and that gets us 6. So that means that the molecular formula is 6 times bigger than the empirical formula. So C6H12O6. That's the molecular formula in this case. In my first quantitative chemistry video, we took a look at concentration as an overview. We're now going to look at more in-depth concentration calculations, such as those that you might encounter for titrations. I'm not going to go into the titration method in this video. We'll take a look at that in a separate video. Here we're going to look at the calculations that you get as a result of your titration. So the purpose of a titration is usually to work out the concentration of one of your reactants. You must know the concentration of one of your reactants, but you might not know the concentration of one of the others. So if we take a look at this first scenario, and we are shown that there is hydrochloric acid that has got a concentration of 0.1 moles per decimeter cubed, but we don't know the concentration of sodium hydroxide. However, what we do know is that 20 cm cubed of hydrochloric acid exactly is added from the burette, and that reacts with 25 cubic centimeters of sodium hydroxide in the conical flask. And so we can use all of this information to work out what the sodium hydroxide concentration is. The two things that we need to tie all of that information together are the chemical equation, and that is shown here. HCl is reacting with sodium hydroxide in a 1-to-1 mole ratio and turning into sodium chloride and water, also 1-to-1. But during titration calculations, the products actually, we can put them to one side. It's always to do with the reactants in a titration calculation. Certainly at GCSE level it was. The second bit of information that we need is the grid method. Now this grid is going to look slightly different to the typical grid. It's got the same number of rows and the same number of columns, but two of the rows are different. Where previously we would have had mass and MR, we have got concentration and then volume underneath. The equation that we're about to be using here in this grid method is moles of solution is equal to concentration multiplied by the volume of the solution. Now, some important clarification. Moles is obviously just moles, but concentration is pretty much always in moles per decimeter cubed. And that means that the volume must also be in decimeters cubed. So there's two things to note here. First of all, the actual equation itself, but secondly, the units. And the significance of the units, if we take a look at the data in the question, we've been given 20 centimeters cubed, 25 centimeters cubed. We haven't been given these in decimeters cubed. And so we need to remember that to convert centimeters cubed into decimeters cubed, we need to divide these numbers by 1000. And so the chemicals themselves, we put in HCl and we put in NaOH at the top of these columns. The concentration, well, HCl is 0.1, sodium hydroxide, that's our unknown. We haven't actually calculated this yet. But the HCl is 20 cm cubed, which then when we divide that by 1000 is 0.02 dm cubed. And again, NaOH is 25 cm cubed. We divide that number by 1000 and we get 0.025 dm cubed. The ratio from the equation is 1 sodium hydroxide requires 1 HCl to react with it. And we can see that because there's no multipliers in the equation itself, which means this is a 1-to-1 reaction ratio. And so now what we're left to do is actually the calculations. So moles, as we can see up at the top, is equal to concentration multiplied by volume. So 0.1 multiplied by 0.02, and that gets us 0.002 as our moles of HCl. Then we need to look at this reaction ratio. It's 1 to 1. And so what that means is, however many moles of HCl we've got, that's the number of moles of sodium hydroxide that are required to react with it. So that means that these two numbers, whatever they turn out to be, they need to be the same number. So 0.002 moles of sodium hydroxide required as well. And last of all, we need to rearrange our moles as equal to concentration times volume expression. That means that we need to divide both sides by volume, and then they'll cancel out on the right-hand side. So that means concentration is moles divided by volume. So our 0.002 needs to be divided by 0.025, and that gets us a final answer of 0.08 moles per decimeter cubed as our concentration for sodium hydroxide. It's often worth doing a check to see if the answer that you found is reasonable. Take a look at the volumes of hydrochloric acid and sodium hydroxide. The sodium hydroxide has got a larger volume than the hydrochloric acid has, even though the mole ratio is 1 to 1. And so that means that we would expect the sodium hydroxide to be more dilute than the hydrochloric acid. And indeed, 0.08 is smaller than 0.1. And so this seems like a reasonable answer to this calculation. I thought we'd take a look at one second example here that you could have a go at yourself, so you can pause the video and try and work this out for yourself, and then I'll go through it in just a moment. Assuming that you have paused the video, we can take a look at the equation now. The first difference in this equation is obviously that we're working with sulfuric acid in this question, and as a consequence of that, the ratio has changed. So in our chemicals row, we're going to put our sulfuric acid and our sodium hydroxide, and we're going to transfer from the equation the ratio of 1 to 2, and that's going to be really significant in a moment. The concentrations and volumes have also changed. Sulfuric acid is now 0.04 moles per decimeter cubed, and the sodium hydroxide is still the unknown. The volume of sulfuric acid is 30 cubic centimeters. Of course, that needs to be in dm cubed, and the sodium hydroxide is 25 cubic centimeters. That also needs to be in dm cubed. So again, we're dividing both by 1000. So then when we do moles is concentration multiplied by volume for the sulfuric acid, we get a final answer of 0.0012 for the moles of sulfuric acid. And then when we take a look at the ratio, 1 mole of sulfuric acid reacts with 2 moles of sodium hydroxide. So what that means is, however many moles of sulfuric acid we've got, we require twice as many moles of sodium hydroxide. So in other words, we need to double the number of moles of sulfuric acid that we've got, and that is the moles of sodium hydroxide. So that means that we've got 0.0024 moles of sodium hydroxide. And then finally, concentration is moles divided by volume. So that means that our value that we've just calculated divided by our volume, 0.025, and that gets us a final answer for our concentration of 0.096 moles per decimeter cubed. And if we take a look at the equation and the ratio, we are expecting twice the number of moles of sodium hydroxide. And since the volumes are similar, we're expecting the concentration of the sodium hydroxide to be approximately twice as much. And it is approximately twice as much. It's a little bit more than twice as much. So this seems like a reasonable answer to this calculation. Okay, I hope you found this Head Start video useful. If you want to find out more about A-level chemistry for this topic, check out some of the links in the description. If you found it a bit tricky and want to go over this topic a little bit more slowly and in more detail, I'll put links to my GCSE explanation videos in the description as well. But that's all for now. I'll see you again soon.